In the previous slides, we discussed pseudomorphic growth, where a thin epitaxial film elastically deforms so that its lattice spacing in the plane of the interface matches that of the substrate. As long as the film is sufficiently thin, the crystal can maintain this coherent strand, meaning the atomic rows remain perfectly continuous across the interface. So this type of coherently strained crystal is called pseudomorphic, since it takes on the morphology or form of the substrate. In this case, the lattice constant of the substrate. However, this strained configuration stores elastic strain energy in the film. As the epitaxial layer becomes thicker, the total strain energy continues to increase. Eventually, the system reaches a point where maintaining coherent strain is no longer energetically favorable. At that point, the crystal relaxes the strain by forming structural defects known as misfit dislocations. A misfit dislocation is a line defect that forms at or near the interface between two materials with different lattice constants. As shown on the slide, it can be visualized as a location where the regular atomic bonding across the interface is disrupted, producing missing or dangling bonds in the lattice. These dislocations allow the lattice mismatch strain to be partially relieved. So let's consider the example shown here. A silicon germanium layer grown on a silicon substrate. We know that silicon germanium alloys generally have a slightly larger lattice constant than pure silicon. When a silicon germanium layer is first grown on silicon, the film initially grows pseudomorphically, meaning it is compressed laterally to match the silicon lattice. But once the film thickness exceeds a certain value, called the critical thickness, the strain energy becomes large enough that the system lowers its total energy by forming misfit dislocations at the interface, as shown here. So you can see the progression illustrated in the diagram. If the film is very thin, it remains coherently strained and no dislocations are present. As the film becomes thicker than the critical thickness, dislocations appear at the interface and the lattice mismatch begins to relax. So while misfit dislocations help relieve strain, they are in general undesirable in semiconductor devices because they introduce defects in the crystal lattice. These defects can act as, for example, non-radiative recombination centers, scattering centers for carriers, and leakage paths in electronic devices. So, controlling or avoiding misfit dislocations is a major challenge in heteroepitaxial growth. Now let's look at a direct experimental evidence. This slide shows a transmission electron microscopy (TEM) image of misfit dislocations formed in gallium antimonide layers on top of a gallium arsenide substrate. First, please notice the scale bars. In the upper image, the scale bar is 5 nanometer. In the lower, it is 1 nanometer. So we are looking at atomic scale resolution in the bottom panel. In the top panel, you can clearly see a dark horizontal line at the interface between gallium antimonide and gallium arsenide. The red arrows indicate the positions of interfacial dislocations spaced periodically along the boundary. These misfit dislocations are line defects. They appear brighter in the image, and in this image they oriented perpendicular to the page. This periodic spacing is not random. It corresponds to how frequently the lattice must insert an extra atomic plane to accommodate the mismatch. Now look at the lower panel. It shows atomic resolution contrast where in the gallium antimonide region we have 13 atoms here, and in the adjacent region, which is the gallium arsenide substrate, we have 14 atoms over the same projected length. This difference directly visualizes the lattice mismatch. In other words, over a certain lateral distance, the gallium antimonide lattice accommodates one fewer atomic spacing than the gallium arsenide lattice. To compensate for that mismatch, a dislocation forms. So we have one misfit dislocation here and one misfit dislocation here. Now let's connect this back to the formula for lattice mismatch. We know the misfit parameter or mismatch parameter f is equal to a sub s minus a sub f divided by a sub f, as shown in this expression. If f is small, dislocations are spaced far apart, and if f is very large, then dislocations are closer together. So from a materials engineering standpoint, a larger mismatch leads to higher dislocation density. And the higher the dislocation density, then the worse the device performance. All right, so this slide is important because it moves us from abstract lattice diagrams to real experimental observation. You are not just looking at a schematic defect, you are seeing atomic planes terminating and shifting at the interface. That is the physical manifestation of lattice mismatch. Now let's consider the situation shown on this slide. Suppose we want to grow a material with a significantly different lattice constant on a substrate. For example, growing gallium arsenide 0.6 phosphide 0.4 on a gallium arsenide or germanium wafer. If we attempt to grow it directly, the lattice mismatch may be too large, leading to high dislocation density. So what do? We introduce a graded epitaxial layer. So instead of abruptly changing composition, we gradually vary the alloy composition over some thickness. For example, starting from pure gallium arsenide right here, we slowly increase the phosphorus content or composition X in gallium arsenide 1 minus X phosphide X until we reach the desired composition. This creates a gradual change in lattice constant rather than a sudden jump. And in the example given here, a graded layer of approximately 25 microns may be required before growing the final epitaxial layer, perhaps 100 microns thick on top of it. And let's look at the diagram on this page again. As we have discussed earlier, different binary compounds lie at different positions in this map. When designing devices such as red LEDs, we choose materials based on band gap. However, we must simultaneously satisfy lattice compatibility. So this is the core engineering trade-off in heterostructure design. The electronic optical properties depend on the band gap, while structural compatibility depends on lattice constant. So if we cannot find a perfectly lattice-matched material with the desired band gap, we use graded layers to transition gradually between lattice constants. So the graded region distributes strain over a larger thickness, reducing the density of dislocations that propagate into the active region. And please note that the graded epitaxial growth technique is essential in LED fabrication, laser diodes, multi-junction solar cells, and high electron mobility transistors.